let's start recording and then I'll cut it later. Okay.
Well, if it were true, then that would mean you could make a graph with 17 vertices, each with 3 connections.
Okay. Okay. Each with, let's call them degree 3. Can we write it degree 3? Right? Would that be, so notice what we're doing, by the way. And this kind of will become later when we'll discuss planar map coloring. We'll be answering questions like, is it possible to color the map of the United States, for example, where each state receives some color and no 2 bordering states receive the same color? What is the smallest number of colors that you can use to color the map of the United States? And turns out the answer is 3. Then we pose another question. Is it possible maybe the US states configuration is such that it's possible to do it for the US with 3 colors, but not possible maybe for some other country? Or if it's possible for every country in the world, can you imagine a country that's subdivided into either states, I don't know what their political arrangement is of their society, but let's say it's provinces or states, whatever it is, in such a way that no 2 bordering countries receive the same color so that a person looking on the map can distinguish between the 2 entities. And you use the smallest number of colors possible to color this map. Okay. So what we'll find helpful in that situation is to associate a vertex, as you've just suggested, with each one of those states or provinces, and draw an edge between the 2 if they are bordering each other, and not draw an edge between the 2 if they're not bordering each other. This graph associated with the map will be called a dual graph to the map, to that map, right? So we'll introduce that special terminology. It will be called a dual graph, so this dual. So what you're suggesting as we go along, you're suggesting a construction of a dual graph. It is a model of the problem that helps you think through the problem. That's why you thought about the graph, right? So somehow this graph will help you think through the actual problem, whether it is possible for such a map to exist in the world. So yes, you have 17 vertices. You've associated each province with a vertex, and each vertex, it has degree 3. That is, each province borders 3 other regions, 3 other provinces. So then you're suggesting then the total number of the total number of degrees, sum total, let's call it, sum total of degrees is going to be 17 times 3, right? Which is 51. But whatever it is, it's an odd number, which is odd number. Odd number. This is an odd number. But by the handshake lemma, we now know that that number, the sum of all degrees, has to be twice the number of edges. So on the other hand, by the handshake lemma or theorem, sum of degrees must be even. Must be even. Must be even. So we have arrived at an absurdity, which is that that an even number equals an odd number. So on the one hand, by the handshake lemma, the sum of all degrees must be even. On the other hand, in this particular situation, the sum of degrees is odd. Therefore, my assumption must have been wrong. And what was my assumption? My assumption was that such a graph exists. Such a map of Klopstokia can be drawn. So a map exists. That is, a graph with 17 vertices, each of which has degree 3 exists. That is the only assumption that I've used, which by this chain of logical deductions landed me at an absurdity. Therefore, that assumption has to have been wrong, and therefore such a graph does not exist, I conclude. Okay, that in the classical times, that argument that I just gave was called reductio ad absurdum. Okay, reduction of an argument to an absurdity. And today the same terminology is used. Okay, or proof by contradiction. So proof by contradiction is a better term. Is a modern term. I mean, it's the same term, but not reductio, but reductio. But my Latin is not good, so I will make mistakes in pronunciation. So that's why I'm trying not to use Latin. But these are old arguments, like proofs by contradiction and so on and so forth. Anyway, okay, so that's the review of last time. Now let's talk about new things. Okay, so now we'll be dealing with undirected graphs, and we'll give a classification of these graphs. So certain kinds of those graphs will be useful to model certain real-world situations more so than others. So one of those graphs that is useful is called a complete graph on n vertices. So what does that mean? So suppose you have n vertices. Let's take n equals 3. So 1, 2, 3. Here's every pair of those vertices. Every unordered pair of those vertices is connected with an edge. Question is, how many edges will I have? Well, if it's only 3, then I see which pairs I have. This is a pair, so A, B, C. AB is a pair, well, connected with an edge. BC is a pair, connected with an edge. AC is a pair, connected with an edge. A, B, C, D. A, B, C, D. Now n equals 4. How many possible pairs can I have in a set of n elements? In this case, I've drawn n equals 4, where the order of the elements does not matter. And you tell me if the problem that I've just posed seems in any way familiar to you. Maybe you've seen something in, say, 1166 or an introductory probability course where you talked about combinations of things, where somebody told you, well, you have this bag of n marbles. You reach in and take k at a time. So what does it mean that order does not matter? Let's say you have a bag of like n items and you reach in and take 2 at a time. So if I select A, marble A, and marble B, I do it in one grab, it's 2 at a time. Or if you want to do it a repeated experiment, you grab marble A, put it on the table, then you reach in, grab marble B, put it on the table. That's the same draw as if I had gone and drawn B the first time around. Put that on the table, and then the second time drawn A, put that on the table, I still draw AB, okay? You could think of that experiment as something being done in stages. Or you can think of reaching into the bag and drawing 2 marbles, and you draw, let's say, AB, or D and Z, or whatever, just 2 marbles out of a bag of n marbles. The question is, how many different ways are there of drawing 2 elements at a time, in general, k elements at a time? But here we're talking about pairs. So we're drawing 2 elements at a time from a bag, in this case, of 4 elements. Here's my 4 elements. The question is, how many different ways are there of drawing 2 elements out of a bag of 4 elements where the order of the elements does not matter? Right? And by the way, notice that I'm drawing 2 elements, grabbing and reaching, drawing 2. That will in a moment correspond with the situation where you have no self loops in the graph. And first of all, why did I even say the last sentence? So what do I mean by grabbing 2 from a bag? In our graph terminology, what would that correspond to? Let's start making some connections with the graphs. Seems some kind of an abstract setup, right? I'm drawing like reaching something, taking out of the bag. What does it have to do with graphs, like completely? And what graph? Where is the graph here? What am I doing? Can people help me?
You're choosing 2 vertices to create an edge, assumingly?
Yes. So choosing 2 vertices corresponds to an edge. So if I count all the possible ways of choosing 2 elements at a time from this bag, would people agree that this would people agree with the following? Any draw of 2 elements, 2 marbles from the bag, corresponds, as you've just said, to drawing an edge between some 2 vertices, right? Of all the possible ways of drawing 2 marbles at a time would correspond to all the possible ways of drawing edges in a graph on n elements. Does that make sense? Right?
Yeah.
So the total number of edges that one could possibly draw in a graph on n vertices, the maximum possible number of edges, that is, all possible edges that you could have on a graph on n vertices, corresponds exactly to the number of ways of selecting 2 items at a time from a bag of n elements. Do people agree? Does that make sense? There's a 1-to-1 correspondence between an edge and selecting 2 marbles from a bag of n elements where the order doesn't matter if the graph is undirected. Does it make sense to people? Right? Yes, no?
Yeah.
If no, then how? Okay. So is there anyone for whom this doesn't make sense? in some, so it's okay to not make sense. I mean, let's discuss it.
I mean, it makes sense.
Makes sense. Okay. Okay. So then, so one way to go for us would be, let's remember the formula of taking the less preferred way for us would be, oh, do you remember that formula? You passed that test. Why do you not remember the formula would be one way to go. That's not our preferred way to go. Okay. If you forgot the formula, that means you haven't learned it. Maybe you learned it to ace the test at that time, but if you've forgotten it by now, then maybe we should look at it again. So do people remember what did we call anything in 1166, such quantities of drawing k elements at a time from the set of n elements? You either used this notation, something like, you called them these combinations, right? So you had this, like you covered this part in 1166, where you talked about permutations, combinations, bit of combinatorics, right? Did you have this part? Right?
Yeah.
Okay.
Yeah, we did combinatorics.
Okay. So did you have this symbol, which I personally don't use because probability you prefer use this symbol. But anyway, whichever ones you used, either one.
Yeah, we saw those.
Which one? This one?
Yeah, we saw the CKN. Yeah, that.
Yeah. Okay.
We also saw the parentheses version.
Okay. Yeah.
Before.
Yeah. Those mean the same thing. These are the same. So choosing k items from n, k at a time. The order does not matter. That's what I mean. Combinations of k items taken from a bag of n elements at a k at a time. So either you remember the formula or you can Google it quickly and tell me what it is. So if you Google, you'll come up with something like this. Okay, this is this one, choosing k elements out of n. That's this number, okay, this number. And everybody knows what factorial is, even if you've forgotten this formula, okay? So you know what a factorial is. So when k is 2, now we're reaching in and taking 2 items at a time. So when k is 2, okay, k is 2, and n is, let's say, 4. Okay, so we're choosing from 4, we're choosing 2 items. This reduces to 4 factorial, 2 factorial to 2 factorial, and this is going to be 6. Okay, so you cancel these things out. It's 4 times 3 divided by 2 factorial is going to be 6. If you plug it into your calculator, it's going to be 6. Okay, you can trust me in that. That's 6. So apparently, the maximum number of edges that I can draw in this graph here, if our arguments made sense, if I didn't engage in sophistry of some sort, and that my arguments didn't have any flaws, and if we all agree, okay, if the argument was what they call sound, then I should be able to draw exactly 6 edges here, and no more, no less. Okay, so that's all. If I draw all the edges, so A to B is an edge, B to C is an edge, C to D is an edge, A to C is an edge, and A to D is an edge, and B to D is an edge. That is 6 edges. You can't draw any other edges. It's exactly 6 edges. So all the edges, and I know I'm going to have 6 of them because of this argument, because I knew it from there. And by the way, this K4 is right here. So the number of edges in K4 is going to be 4 choose 2. Now, suppose you didn't know the formula. Okay. Now this wouldn't be a math class if I did. Now you know the formula. Let's just move on. Then it's just I might as well be reading from the slides. So now let's stay in this a little bit more because it is a math class after all. Now suppose you have no idea, you haven't taken 1166. And this class, by the way, or 1168, was it 1166 or 68? 66, right? You haven't taken that class. And you're just given a smattering of points on the plane. And you want to know what's the maximum number of edges you can draw in this situation here, in this situation. This is a new situation. Okay, now I have 5, but in general, n. So n equals 5 here. Okay, and you kind of sort of already know the answer. The answer is given here. But I want to methodically account for all the edges. You're given, you already know the definition of what a simple graph is. You have n, in this case, 5 vertices, and you want to account for all the possible number of edges that you can possibly have. And of course, no multi-loops are allowed. You can't have 2 edges between the same pair of vertices. Each pair of vertices is connected by exactly 1 edge. How do you account for all the edges? Okay. Okay, so how would you start counting? Like you have no idea about any choose, or even if you know, just don't see that connection for the time being, and you just want to count the number of edges. What do? Let's number them. 1, 2, 3, 4, 5. Let's take 6. So n equals 6. So first of all, is 1 connected to all these n minus 1 others? Right? 1 is connected to n minus 1 others. Those are the edges. Those edges have to be present here. Now 2, let's use blue for that one. 2 is connected to n minus 1 others, right? Think of these guys that came in and shook hands. Like there's every possible handshake right now in this room, and I want to count the maximum number of handshakes possible in the room. That's what I'm counting for. Now, two shook hands with 1 and 3 and 4 and everybody else. So 2 performed n minus 1 handshakes too, but one of those handshakes with 1, that handshake with 1 was accounted for by 1 in my tally. So when I account for 2's handshakes, I'm really adding n minus 2, right? Do people agree? So I'm accounting now for all the handshakes that 2 performed, and here are all the 2's handshakes. It includes the handshake with 1, but that was accounted for here in this term. Then I move on to 3, and I ask 3, how many handshakes did you perform? And on my tally, 3 tells me that 3 performed n minus 1 handshakes. That is 5 handshakes in this case. For out of 6 people, with all 5 others, 3 shook hands. Okay, so he said, okay, so I performed n minus 1 handshakes. But the 2 people just before 3, this guy and this guy, they told me about those handshakes. This one and this one already accounted for. So now 3 gives me this, this, this. That's it. That many handshakes. N minus 3 handshakes, and so on. So I continue, I get to 4. Ask 4, how many handshakes did you perform? 4 will say n minus 1, but I'm accounting for all the handshakes without counting any handshakes twice. So 4 will tell me for 5 and 6, and that handshake with 1, with 2, with 3, that's already accounted for. So it will say n minus 4, and so on. Until I get down to 1 handshake. When I ask 5, how many handshakes did you perform? 5 will say, well, I performed n minus 1 handshakes, 5 handshakes too, but all these previous handshakes have been accounted for. So all I have to draw is this for the n minus 1st guy. And for the 6th guy, I put in 0 in here. So in this expression, in this sum here, in this sum, the total number, this is the total number of edges, where each edge is accounted and counted only once. So this gives me the exact number of total number of edges, the exact number of edges. So what is, now let me ask you again. So apparently this, well, that's 0 plus, okay, 0 plus 1 plus 2 plus blah, 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 plus n minus 2 plus n minus 1. What is that sum? So do you remember, like from high school, that you actually called this guy something? This kind of
n times n plus 1 over 2?
Yes, yes. In this case, it ends at n minus 1, so it's going to be n times n minus 1.
Minus 1.
Yeah, that's the one. Yeah. So this one is called arithmetic progression, but the name doesn't matter. So this sum. Oh, by the way, we proved something like this, right? In induction, in the part of induction. So this could be proven by induction, which is not the best proof, but you know, it can be proven by induction. But anyway, the sum is that. And maybe I'll show you a prettier proof if we have time. But anyway, you know that sum to be that. Of course, that sum gives me the maximum number of edges that a graph, a simple graph, an undirected graph, a simple undirected graph on n vertices can have. That's one way of accounting for all the edges. Another way of accounting for all the edges is by thinking about drawing an edge as selecting a pair from a bag of n vertices. That's exactly, it's just a model in your mind and how to account for all the edges. Two different models, they count the same thing. Therefore, this quantity, choose from n, choose 2, this quantity, n choose 2, has to be the same as this. And it is, of course. It's, by the way, another way of proving why choosing 2 items at a time from n elements, the total number of ways of doing that is going to be that sum of this arithmetic progression. Okay? Because these are 2 different ways of solving the same problem. So therefore, the 2 entities have to be the same. There's no other way. Does that make sense? Right? The point that, so what we have done is we had a lengthy discussion, but it was worth it because, okay, okay, so we don't need to justify why it was worth it. I mean, that's the activity, that's the math course. I mean, otherwise you could just, okay, here's the formula. It's not like that. Okay, so let me erase that. So here's an example of 6. So if you take this, this is a graph. This is called a complete graph on n vertices. Complete graph on n vertices is a simple undirected graph that has all the edges it can possibly have. That's called a complete graph on n vertices. So here's a picture of a complete graph on 6 vertices. Every pair is connected. Here's 1 and 5, and so on and so forth. And if you have n vertices, you have roughly, not roughly, but roughly it grows with n squared, but you have exactly n times n minus 1 over 2 edges in such a graph. Okay, that's it. That's a complete graph. Okay, so that's one kind of a graph. Now we also have another kind of a graph. That other kind of a graph we'll call a cycle graph. Here are examples of cycle graphs. Okay, in a cycle graph, you number the vertices 1, 2, 3, 4. In this case, it's v1, v2, vn, n vertices, a cycle graph on n vertices. And you connect each vk to vk plus first, starting from k equals 1, until you get to k minus 1, until you get, so this one is going to be 2, then blah, 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 blah. K gets to n minus 1. This is going to be n. And when k gets to n, it cycles around. You have another edge like vn. So that's for all these edges like that, vk to k plus 1, when k ranges from 1 up to n minus 1. And then you have an edge vn, v1. That's an edge. Okay, that's a way of writing down this kind of graph that we'll call cycle graphs. That's much easier to represent it in a picture. So here's a picture of C6. You have 6 vertices. Start numbering 1, 2, 3. Okay, let's call it V1, V2, V3, V4. I don't know, V5, V6. So V1 is connected to V2, V2, V3, V4, V5, and so on, V6. And V6 finally is connected to V1. That's called a cycle graph. It has n vertices. Cycle graphs and n vertices. Okay, that's clear. How about another kind of graph? And let me give you a heads up. This is where people, for some reason, tend to lose a point or two on the quizzes, and please don't do it. There's no reason to lose a point here. We have a notion of a wheel graph on n vertices. Okay, it actually, so W5 actually has 6 vertices, one more. Well, how is the wheel graph constructed? Well, the name wheel gives it away. You have a bunch of vertices, in fact, n minus 1 of them, 4 vertices. So in W5, you have 1, 2, 3, 4, 5 vertices around the wheel on the periphery. And then you have the center of the wheel, the hub, call it, connected with spokes to others, to every other vertex. Okay? So by the way, what's the sum of degrees of the vertices in C6? What is the sum of degrees? What's the sum of all degrees?
12.
Sorry. Yeah. Okay. Is it 12? Good point. I guess that, I don't mean it to make it a trick question, but I guess it's a trick question. So 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Right, so each one has degree 2. So yeah, okay, so that's not a trick question. How about W3? Okay, W6, take Wn. Let's take Wn. What's the sum of all degrees? Okay, let's take W. I don't want to take the one that's already drawn here because people can count. In general, I want an expression for the number of sum of all degrees of Wn. So, yeah. So is it clear how it's constructed, right? You take a cycle graph on n vertices, add one more vertex to it. So Wn actually has n plus 1 vertices. So okay, here's W6 has 7 vertices and so on. So Wn, the wheel graph, is the wheel graph on n plus 1 vertices, really. So please keep this in mind because there's like, I know one question that comes up on quizzes or tests or the midterm, whatever, and it has this question. So please, I'm telling you now, Please remember, so this Wn has n plus 1 vertices. It's the only place kind of an oddity, right? So Wn means you have a cycle in n vertices plus the n plus first vertex. That's the hub of that wheel. Okay, and so what's the sum of all the degrees? So for each of these n guys, you have a degree 3, right? Because 2 from the cycle, and then the one spoke that comes in from the hub. So each one has degree 3. These guys has degree 3, degree 3. So 3 times n. Okay, so, or maybe we should write it down, n plus n plus n, like 3 plus 3 plus 3, n times. That's 3n. And then, what do we have again? How many, what's the degree of this guy? N, right? So it's, do I have an odd number? How many, is it consistent with our observation earlier? That we must have an even number of, as the sum of the degrees of all the vertices must be even.
Professor?
Yeah.
What do you add the end there? At the end?
Because, okay, so what's the degree of this one? The hub.
Oh, okay.
So this is the hub's degree.
Gotcha. Yeah, it's 6. Okay.
Okay, so each vertex that's on the periphery has degree 3. This guy has degree 3. This guy has degree 3. Everyone. So I have n of those, and then plus I have this guy who has degree n. Okay, so yeah, it's 4n, and it's an even number for sure. There's no other way. That's twice the number of edges. The number of edges in if somebody asks me the number of edges in W, what's the number of edges in W? N. It's not a trick question. It's like half of that, right? So twice the number of edges is 4n. Therefore, the number of edges is going to be 2n. Okay, so that's consistent with what you have. But yeah, okay. Time. What do we have? So I want to talk about bipartite graphs. So I should tell you about Q3. Let me quickly tell you about Qn graph. So let's take Q3. So in general, you take Q sub n is you take all the bit strings of length n. How many such bit strings exist? And by the way, each bit string you make a, okay, so you take all bit strings of length n and make each bit string, like an entire string, is a vertex. Associate that with a vertex in some graph, which in 3 dimensions you can draw. In 4 dimensions you can no longer imagine, 4 or higher dimensions, but you can extrapolate from what you can imagine in 2 or 3 dimensions. We're limited in that regard, so we can only see 3-dimensional worlds. Of course, you can have amazingly beautiful models in higher dimensions, but those can be only mathematically described. I mean, that's just, we just can't see it, just the way we are. But anyway, that aside, you take bit strings of length n. Let's take bit strings of length 3. Well, how many bit strings are there? By the way, by bit string, I mean, each bit position can have either a 0 or a 1. So you have this, and so on. So how many, what's the total number?
2 to the 3rd?
Yeah, 2 to the 3rd, exactly. I shouldn't even write down 8, which is 8, but it's 2 to the 3rd. So that 2 to the 3rd, those 8 vertices, each of these bit strings is a vertex. So vertex, and instead of, I could number it from 1 through 8, but it's much more convenient to do the numbering from 0, 0, 0, 0, 0, 1. That's a more convenient numbering in base 2. And you place those vertices here, like this. Let's call it, I guess, the z-axis. It's kind of odd. You normally have an x-axis here, but let's call it z because it's the way this one is drawn. It's from the book. You could have drawn it differently, but this one, the last coordinate is 1. So this is the z-axis. You have y goes there. Let's say, is that y? Yeah. And then x goes kind of weirdly here. It's just oriented differently, but it's the same 3-dimensional space. So, these become vertices. You have 8 of them. And there is an edge between 2 vertices in this graph if the 2 bit strings corresponding to those 2 vertices differ in exactly 1 position. For example, there is a vertex, there is an edge between 0, 0, 0 and 0, 1, 0 because these two vertices differ in exactly this position, the second position, then there is an edge. There is an edge here. There is no edge between, let's say, take 1, 1, 1 and 0, 0, 1. There is no edge because these guys differ in two positions, this position, this position, this position, this position, right? And in general, when you have bit strings of length n, you can be quite methodical about this. This will correspond to a cube, hypercube, in n dimensions. Okay, in this case, this is a hypercube in 3 dimensions. In general, in n dimensions, it will look something right like this. If you want to imagine, obviously it's impossible, but it's called a hypercube by extrapolation from the 3-dimensional case. Okay, that's called a hypercube. It's useful in modeling certain things in computer hardware and so on. Let's not stop on that because we have to move on. I have to give more definitions. Okay, now I want to talk about bipartite graphs. So a graph is called bipartite if the set of its vertices can be partitioned into 2 non-overlapping subsets. Okay, but when I say the word partition, I mean it can be split into 2 different subsets that do not intersect one another and whose union is the entire set V. So I have a graph G. What's a graph? Well, a graph is a set of vertices and the set of edges. And what I'm saying is that V itself can be partitioned into V1 and V2, 2 non-overlapping sets, such that, so their union is going to be V1, V, okay? And so their union is going to be V. And their intersection is going to be an empty set, okay? That's what we mean by the word partition. The word partition means this. Partitioning V into V1 and V2 means that V1 and V2 do not intersect and their union is the entire set V. So if you have a graph on n vertices, and those vertices make up the set V, and if you can partition V into V1 and V2 in such a way that if there is an edge in this graph between the 2 vertices, then those 2 vertices are in V1 and V2 always. Right? Notice what I just said. It takes a minute to parse this. I didn't say that if vertices, I didn't say that if you take 2 vertices, V1 and V2, where if you take 2 vertices, V1 and V2, where this V2 belongs to the set V2, and where this V1 belongs to the set V1, I did not say that there would be an edge between them. I didn't say this. I said the converse. I said that if there is an edge between V1 and V2, then V1 belongs to V1 and V2 belongs to V2. That's what I said. Okay, that is all. That's it. But we need to see examples. Okay, so in general, what you'll have is you have V1, V2. Okay, so let's go with V3. That's a set of vertices here that belong to V1. And then you have, let's call it actually U1, U2, U3. Maybe you have U4. So you have a bunch of vertices here in the set V2. Okay, all these guys, V1, V2, V3, and U1, U2, U3, and U4, all these 7 vertices make up V. If there is an edge, the edge can be only in between the elements from the opposing sets, from the different sets. This is what a bipartite graph is. It doesn't say that there is always an edge between the 2. All it says that there cannot be an edge between 2 vertices that belong to the same partition. Does that make sense? That's what a bipartite graph is. Essentially, you can color the vertices of the entire graph, all of these V, all the elements in V, in 2 different colors, in such a way that if 2 vertices are of the same color, there is no edge between those 2 vertices. And if there is an edge between 2 vertices, those 2 vertices have to be of opposing colors. And again, as a remark, I'm saying that I didn't claim the converse of this. The converse of the last statement that I just made is that if 2 vertices have different colors, then there is an edge. I didn't say that. I said if there is an edge, then the vertices, the endpoints, are of different colors. Okay. Anyway, we'll see examples. So please don't think that I'm splitting hairs. It's kind of like that's what it is. So okay, so here's an example. This one, V1 and V2, this is a bipartite graph. This is how you would normally draw a graph. There is no edge between anything inside any one of the two sets. The only edges you see are between vertices of opposing sets. And maybe not all edges exist. For example, V3 is not connected to V6, but if it were, it would still be a bipartite graph. But every time you see an edge, that edge is between vertices from the opposite sets. That's okay. I think I said it 3 times, so I shouldn't have. Maybe it's too much. Okay. So now my question to you, is C4 bipartite? Is graph C4 bipartite? So help me out. We need to wrap this up in like 20 minutes, less than that. Is C4 bipartite according to our definition?
Yes.
Okay, how so? Well, why? That's correct, but why?
If you take like the top left diagonal node and the bottom right diagonal node and you put those in your left set,
okay,
you can put the other ones in the right set.
Yes, that's exactly right. Let's actually number these guys. Let's call them 1, 2, 3, 4. So I can draw this graph C4 differently. I can put 2 and 4, as you've suggested, in the left set. So that's how I'll do it. And then 1, 3 in the right set. So what I have, I only have connections between, I have a connection between 2 and 1. I have a connection between 4 and 3. I have a connection between 2 and 3. And I have a connection between 4 and 1. This graph is C4. It's just drawn differently. So if not today, next time we'll start discussing what does it mean for the two graphs to be the same. We'll call this guy and that, well, they're clearly the same in some sense. We'll want to be very precise what that sense is. We'll call that sense in which these two graphs are the same isomorphism. We'll have a special term for the sameness of two graphs. We'll call them isomorphic. But anyway, you're absolutely correct. That's the way this graph is bipartite. Is C6 bipartite? This guy. Okay, so if I put 1, 3, and 5 in the same set, and if I put 2, 4, and 6 in the other set, then what's the connections that I have? So this is my partition. These are all these vertices. Okay, this is my V2. This is my V1. Okay, and V1 and V2, they make up the entire V. Okay, and their intersection is clearly an empty set. They have nothing in common. That's what we mean by partition. What are my edges? Well, 1 is connected to 2. 2 is connected to 3. 3 is connected to 4. 4 is connected to 5. 5 is connected to 6. 6 is connected to 1. Okay, it's a bipartite graph. There are no connections between the red vertices. Okay, there's no edge whose endpoints are both either red or both blue. If there is an edge in this graph, its endpoints are of different colors. That's why it's a bipartite graph. I can color it in such way. Right, so that's a bipartite graph. Is C5 bipartite? This guy. So help me out, I'm stuck. Kind of C5 bipartite. And maybe we can actually generalize, actually do some math after this. Once we make those observations, and we're ready to do math. Any ideas?
Not bipartite.
No, why not? That's correct, yes, but why not? suppose I were able to color. So let's suggest an algorithm for coloring the vertices. Okay, so let's start anywhere. Without loss of generality, I can start at this vertex. Could have started anywhere else. And methodically, let's go around, let's either counterclockwise, clockwise. In this case, let's go clockwise. So 1 is going to be a red, let's say red vertex. Then because 1 is connected to 2, 2 has to receive a different color. So I'm looking for a partition of this set. Then 2 has to be of a different color. Now 2 is connected to 3 as well. But because 3 and 1 are not connected to each other, they can have the same color. So I'm going to put 3 in the same set as 1. So I'm going to color it as red. 3 is connected to 4. They better have different colors. So 4 has to be non-red. But because 4 is not connected to 2, it can be blue, just as 2 is. Oops, just as 2 is. So 4 can be blue. Then 5 is going to be red by the same argument. Then I'm back to 1. So 5 and 1 are connected if I have 5 vertices. So this scheme didn't really work. Now 5 and 1 are connected and they received the same color red. That's not a, that can't make it a bipartite graph. Okay, so somehow I wasn't able to color this in 2 colors. Is the graph, okay, well, first of all, can from this argument alone, this would be sophistry. From this argument alone, can I conclude that this is not bipartite? Now, well, this particular scheme didn't color it. I need to strengthen my argument somehow and let you think about it. But you can generalize this easily. If you go around, let's say clockwise, if you have an odd number of vertices, if you pursue this scheme of coloring the vertices this way, then the odd vertex will have to receive the same, according to this scheme, the odd vertex always receives the same color as 1. And the eventh vertex receives the same coloring as every other eventh vertex. So if the total number of vertices in your graph is odd, then the last vertex, which is the odd one, received the same coloring as the first vertex. But because the last and the first are connected, that scheme does not allow for two coloring of the graph. Right? Does that make sense? Or it doesn't make sense?
That makes sense.
Yeah, it makes sense, right? So in general, if you have, okay, so C5 is not bipartite. Is C7 bipartite? By the way, this argument needs a little bit strengthening. You can see that if you have, so what we have proved without any doubt is that if this cycle graph has an even number of vertices, then it is bipartite. Okay, but the theorem is that the cycle graph is bipartite if and only if it has an even number of vertices, right? If and only if it has an even number of vertices. So C7 is not bipartite and C2166 is bipartite because you can follow the scheme to color the vertices in 2 numbers. Okay, finally, okay, we have to move on, but luckily this is the last slide. Now we have the notion of a complete bipartite graph. In this case, we are saying that if 2 vertices belong to these two different sets, then there is an edge between them. Okay, before we claimed only the converse of this, that if I have an edge, then the endpoints are of different colors. Now we're claiming that if the endpoints of 2 vertices have different colors, there's going to be an edge between them. So here's an example of K23. So K23 stands for a bipartite graph on 5 vertices, on 2 plus 3 vertices. Okay, it's easier to say 2 plus 3 than to say 5, just to make it clear. So these 3 vertices are blue, they belong in this set, and those 2 vertices are red, and they belong in this set. And if 2 vertices are from the different sets, then there is an edge between them. So every possible edge is drawn. Every legally allowed edge is drawn in this graph. So what's the total number of edges in KMN? So you have KMN. So you have, here's M vertices. So let's actually use red here. M. So let's use M of these guys. And then you have, let's say, in general, a different number, n of the other guys. So what's the number of edges here? In KMN. So if two vertices are of opposing colors, there is an edge between them. All we need to do today, the last thing is answer, how many edges does this one have? So help me out, I'm kind of stuck. But I know that for like every vertex in, let's take this red set here, each one of these M vertices, like this guy, take this guy, it's connected to every one of these N guys. It's connected to every one of the N guys. That holds true for every one of these M red vertices. Each one of the red M vertices is connected to every one of the blue N vertices. So what's the total number of edges that I can have? You got it. You
M times
the answer, you just have to say it.
M times N?
Yeah, M times N, right? So this guy has N connections, this guy has N connections, and there are M of them. So M times N, or N times M, whatever. That's the number of edges in a complete bipartite graph on N plus M vertices. Okay, so next time what we need to discuss is how to actually represent these objects inside a computer. These are incredibly useful devices for modeling and solving all sorts of problems, like all sorts of problems. So graphs are super useful. Next time we'll talk about how to represent them inside a computer. We'll see there are a number of ways. Some have advantages over others, and those others have advantages of the first ones. So there's no clear-cut advantages. Which representation you use depends entirely on the problem at hand, but we'll look at the relative advantages of some representations over others. We'll also talk about what we'll call isomorphism of graphs, which is the sense in which two graphs can be called the same.